Okay, hello guys, welcome back. So today we'll have a better look at linear regression that we started out with in the previous video. So I'll go over the problem once again. So in linear regression, the problem that as we have defined it, it boils down to finding a line of best fit for the data that I have given you. And purposefully, the data I have given you it looks like it can almost fit into a line. I mean, with slight deviations. And so the model we'll be using it's of this form. Y hat, that is a prediction as a function of your input x, is w naught plus w1x, y equals mx plus c type of thing. Alright, so as we saw before in the learning algorithm, what we are doing is trying to minimize this function over here. This is called a loss function, by the way. So this is a loss function we have defined for an aggregate of points. For a single point, this loss function, which also serves as an evaluation metric, will be the distance between the y values basically. And so when we are minimizing the aggregate or the average of the y values, then basically I showed you that it's like solving a system of two linear equations, and which becomes very tedious. So the goal of this video is to actually show you how we can write it in a much more cleaner and prettier way. And why would we even want to do that? So the first answer is the notation is compact. Second is it'll be a bit more intuitive when I start explaining higher level concepts later on. And it's compatible with vector and matrix calculus, which I really feel everyone should get familiarized with, because as we move on to more complicated models, this is what we'll be using. I won't be differentiating term by term and showing you. Okay, so let's start out. Y hat, that's the prediction, I can write as w naught plus w1x. Now notice that it can be written as a dot product of w naught w1, that's the vector of parameters, and 1x. So initially the only feature was x, that is the x value, x coordinate that I've given you. But now I've also added a feature called 1. So that 1 feature, it's common across all the inputs, all the n data points, and it's just augmented. So this is a augmented feature vector. Alright, so this can basically be written as w transpose times x. Okay, simple as that. We have already made our stuff more compact than it needs to be. Okay, now we have been given n input features, n inputs basically. So every input will be of the form 1 and x, a column vector of this form. So we can have prediction y1, which is w transpose x1. It can also be written the other way around, because in dot product order doesn't matter. x1 transpose times w is also fine, as I've written here. Yeah, and similarly y2 can be written in the same form, yn as well. So the point being, instead of collecting our predictions like this, why not collect our predictions in a much more compact form as well? So for that we need to define this capital X, which is also called a design matrix, and in that design matrix each row is your input feature vector. You get me? So my design matrix will look something like this: 1x1, 1x2, all the way to 1xn. It will be a n cross 2 matrix, and so in that each row is one of your input feature vectors. Similarly, I can define a target matrix as well, in which each row is your target, that is the y value that you want to find. Each row contains the y value. And similarly, I have a prediction vector as well. If I'm processing, let's say, n points together, I'm finding the prediction of n points collectively together, then each row in this case will also be a prediction. Each row will be a prediction for a particular input, and that can be written in this way. But notice, if you know your linear algebra well, it can also be written as capital X times w vector. And so, summarizing what I said before, for a single point estimate, you can do y hat is x transpose times w. All right, fair enough. But if you want to do batch processing and leverage fast matrix multiplication when you're implementing all this stuff in a computer, then you can do y hat is x being defined such as so, times w, that is the parameters vector. All right, now you want to express your objective function, that is the stuff you want to minimize, in terms of this x and w. That's the next step to go, right? I mean, something you have to minimize, and we don't want to do what we did before. All right, so let's start out with what we wanted to minimize, which is the average of the predicted y and the actual y. So in terms of the graph, so suppose we are considering this point. For this point, the x lies here, and according to the line, the prediction lies here. So y hat minus y whole square is basically the square of this distance. That is square of the y distance between the predicted and the actual value. So we average those for each and every point, because as I told you, we cannot minimize that for all the points together. So we can only minimize it for one point at one time. So if I want to minimize my loss for this one point, then I'll draw a line through here. It will pass exactly through that point, where at which the loss will become 0, but only for this point. But for all the other points, notice that the loss will increase. So because of that, I want to minimize the average loss over all the points. And so in that, I'll substitute the w transpose xi. Okay, compact enough. But now notice from here that this is basically a component. This is one component exactly of xw minus y. Like what is the first component of xw minus y? Xw minus y, like where is xw now? Okay, so I'll just write xw in somewhere you can see. So xw minus y, that's basically x1 transpose w minus y1, x2 transpose w minus y2, so on. All right, you feel me? So look at this. What this ith term in the summation is the ith component of xw minus y, and we are squaring it. We are squaring them and summing it up. So basically that turns out to be the norm of xw minus y, and by norm I mean it's the length of this vector. We just want to minimize the length of this xw minus y vector, which essentially represents the mean of the distances, mean of the y distance between the actual and the predicted collectively. All right, mind you, underneath all this convoluted mathematics, we are still trying to find the best fit line. Okay, so for now I'll end it with this. In the next lecture, we'll actually hammer out the mathematics of how we are going to minimize this. So I never told you that the mathematics won't be involved, okay? So that's your assumption. The mathematics is still pretty involved, just that I have given you a much more compact way to write that mathematics. Okay, with that, I'll see you in the next video.